Okay, hello. I'm Kai. You know me from Carmelia's talk just now, right? When I joined the Zoom meeting and I crashed the train of thought. I'm very sorry about this, by the way. Yeah. So thank you very much for putting together this workshop. I'm a physicist, right? So I'm learning a lot here. This is very educational for me, and I've decided to use my time here to tell you about like what kind of inference tasks we're interested in cosmology, yeah? and also what kind of challenges we're facing. Yeah? And then in the end, I will present a bit of work in progress that I've done with these people here. Sven Krippendorf in Cambridge and Jochen Beller in Munich. Yeah, but so mostly I'm here really to get some feedback from this community here. So please come up to me and talk like over lunch or so, and give me some nudges in the right direction here. Yeah? Okay, so when I was preparing this talk, so many of us have seen, I think, this amazing post-based lecture series that Jeremiah has and his group have initiated. And I was thinking a lot about these three main pillars of Bayesian inference. And I realized that I could have said something about all of them. So in the interest of time, I will restrict my talk to this first one, right? So I will talk about model misspecifications that we have to deal with. But if you ask me later, I can also tell you about how our priors are made up, and everything is very difficult to conclude what we do. Okay, so first of all, kind of what are we interested in? Yeah. So we look at the universe as a whole, and so this, for the main part, has like two interesting questions. Yeah. So one is kind of what is the history of the universe, and the other is what is the universe made up of? Right? And so this is kind of a crash course on what we know about the history of the universe. Yeah. So we know that we started at some point, or we very far in early times, we had some very hot plasma. Yeah. And we know this because we can still observe it. Yeah? So we can still observe what is called the cosmic microwave background, which is what we see when we look very far into the past. Yeah? And so then at some point, structures started to form. Yeah, so this is where you start to see galaxies and stars, and this is mainly what we observe today. Yeah? And over all of this, the universe is constantly expanding. Okay, concerning the makeup of the universe, yeah, so it's made up of only 5% of like normal matter that we would typically understand. Yeah? And then a larger part, 25%, is what we call dark matter, which we need to actually form the structures that we see, to form these large galaxies, large clusters of galaxies. And then the largest part, unfortunately, is the part we understand the least, which is what we call dark energy. Yeah? And so this we need to introduce to drive an acceleration in the expansion. Yeah? And so, of course, we are very interested in for example, characterizing what this dark energy looks like, or what this actually is physically. Okay, and so this is roughly what our inference problem looks like, right? So we start with some parameters that tell us about or parameterize dark energy, for example, yeah? And then we can simulate the universe to some degree. Yeah? So we started some initial conditions, which are perturbations in a homogeneous density field, yeah? And then we pass by, so to say, this epoch where we have the cosmic microwave background, right? We flip on gravity, and this density field starts to collapse. Yeah? And so we see structure in the late time universe. Yeah, so this is the field we actually observe in the end, more or less. Yeah? And we take this field, we construct summary statistics, and this is what we use to then say something about the parameters that enter this forward model. Okay, and data-wise, we are really good at this. Yeah, so we, or politicians, have spent a lot of money in enabling these amazing experiments that are currently running, right? So these can reach from ground-based, like this Vera Rubin here, up to telescopes that we actually shoot into space. Yeah, and so we really have no shortage in data in this regard. Yeah. Okay, and I just want to briefly highlight two experiments that my group is heavily involved in, just to like give you a scope of the kind of data we are talking about here. Yeah? So EUCLID was launched roughly a year ago, and we think that with EUCLID we will actually measure the positions of 20 million galaxies, yeah? And shape measurements of over 1 billion. So this is really big data science, so to say. And another big experiment that's coming is this SKA experiment, which is a radio ground-based telescope in South Africa and in Australia. And so there we expect to collect 700 petabytes of data a year. So this is really difficult. Okay, but when I say that we are good in data, what I mean is that our precision is very good. But one big thing that we always have to deal with in cosmology is that there's only one universe, right? So we have one very precise measurement of our universe, but that's it, right? So I mean, I can try to maybe subsample this or so, or like divide the sky into multiple areas, but at the end of the day, there's one data vector that we have to fit for. Good. So what do we actually have to observe? So there's basically two ways of looking at the late-time universe. One is called gravitational lensing, where you look at shapes of galaxies. So what is happening is I have some galaxy in the background, and the light travels to me, to Earth, through some potential well, through some gravitational force, so to say, gravitational well. What we know happens from general relativity is that these light curves get bent. And so this has an influence on the shape of the galaxy as we measure it. And so this is an example, right? So you can see many of these galaxies here are kind of, seem to be kind of shear. They are kind of pressed together. And by probing this, we can probe actually the entire matter field on the way to us. And the other option we have is to measure positions directly. So this is actually real data. So this is about 15 million galaxies in this picture. So this is what a universe looks like. And we can also measure it on this scale, right? And we can measure galaxies and correlate galaxy positions to construct summary statistics. Good. So when I tell you that the data is so great, then kind of what about the modeling aspect of this? And this is where it gets tricky. So the nicest way of constructing a model for this is to write down something that's analytical. And so we can do this to some degree. We can write down what we call effective field theories. But the problem about this is that they are only valid in a certain length range scale regime. Only on very large scales where these fields evolve slowly. So then if we want to push down to smaller scales of the universe, what we have to do is we have to run very expensive n-body simulations. Very expensive simulations in general, which are numeric. And there we have kind of two options, one that only simulates the dark matter and one that also includes normal matter. And especially in regards to these latter simulations, this introduces a very big problem. So normal matter, what does it do? We all know when we look into the sky, we see stars, right? So we form stars and galaxies. And stars can explode, for example, in supernova. And that, of course, pushes a lot of energy into the surrounding medium. And that, of course, then has an influence on the data that we measure for cosmology. And the same is happening for galaxies as well, right? So black holes in the centers of galaxies can develop these very hot and fast jets here. So this is gas that is expelled out of the galaxy. And of course, this also has an influence on the density field that we measure. Good. So here, maybe I should say something before I show this video. So I'm going to show you now a few simulations that people run, right? And they are all supposed to capture the universe, right? These are the best guesses that we have at what the universe looks like. Okay, so these are 4 simulations. They're being evolved in time. Maybe we should kill the light. So can you see this well? Okay, so blue is gas density, red is gas temperature. Right? And you can see that these simulations do not agree, right? And all of them have been calibrated to some degree to observables. Yeah? And you can see that this is a big problem for us. Okay, and so this is the kind of model misspecification that we're talking about. Yeah, so really, we have a very bad idea of how to model the universe at smaller scales. And I would even say, right? So you could say, okay, my prior is like all of them, so to say, or something that goes over all of them, I wouldn't be even super confident that my true universe lies within this prior here. Okay, but the data is so good, right? And we spend a lot of money, and these experiments are also very good at measuring small scale. So this is an example for this Euclid mission. So here, this is one summary statistic we can construct, which is scale dependent. Yeah. So on the left side of this plot, you see the larger scales of the universe. On the right side, you see the smaller scales. Yeah. And the gray band, the gray error band, is a statistical error that we expect from this Euclid mission. Yeah. And you can see that on small scales, this now gets much smaller than kind of some mock data vectors here that we construct from looking at these simulations. Yeah, so this is a big problem. And you can ask me kind of, okay, what have we done thus far? And the sad answer is we just throw the data away, right? So this is from an older survey, and everything that's gray here large scales are on the right side. Everything that's gray here has been thrown away because of model uncertainty. Yeah? And this looks like it's half of the data vector, yeah, but it's actually 90% of the modes, right? Because you can measure more of the smaller modes than of the large modes in a certain volume, so to say. Yeah? Fourier modes, you can think about it. Yeah? Okay. Big problem. And so now, so this is kind of where we thought about, can these post-Bayesian techniques help us? Yeah? And so here, we've run some preliminary tests. Yeah? So this again is a summary statistic that we can construct from these fields. So here large scales are now again on the left side, small scales on the right side. And we have the C parameter here. Can you see that? Which we can vary, which essentially tells us about the amount of structure we have on small scales. Yeah, so this is exactly kind of the uncertainty that we would expect from these effects. Yeah. And in order to test a post-Bayesian approach, yeah, what we do is we generate some mock data with a certain C value, and then we tell our model a different C value and do not put, so we put a delta prior on it, so to say. Yeah? So we fix the C value in our model to a wrong value. Yeah? And so what we use there for this test is a paper or like a pipeline that comes from Harita, who's here today. I'm sure she can tell you much more about this than I can, but try to anyhow. Yeah. So this is a nonparametric approach where you place a prior on the data generating process itself. Yeah? So you say that you have a prior on your data generating process, which you choose to be a Dirichlet process. And the nice thing about the Dirichlet process is that you know that your posterior then is also a Dirichlet process. Yeah? So the idea here is that you sample from this non-parametric posterior, from this Dirichlet process. And then for every sample that you draw, you minimize some cost function. And so what they choose in their paper, and we just completely took the same pipeline, right? What they choose is this MMD, this mean maximum discrepancy, which essentially is just two integrals, right? One integral over your model, and one integral that mixes your model together with your observations here. Yeah? So here xi are my observations. I pretend that I have more than one, and x is draws from the model. Right? And this is weighted by some kernel function. Okay, and so we ran this test, and it seems that this kind of gets us in the right direction, right? So when we run standard MCMC, so just the standard Bayesian inference. So here, this is the well-specified case. So you can see that the MCMC posterior, or the Bayes posterior, is much tighter than what we get with the nonparametric approach. But we don't care much about that. We care about what happens when we turn on this misspecification. Yeah? And so we see that once we include some misspecification in our model, this nonparametric method really seems to be more robust than standard Bayes. And we also do some stronger amounts of model misspecification. You can see how MCMC is just way overconfident. Yeah? And yeah, so this is kind of the direction we want to go into with this. I would be very happy for feedback about this. I'm sure that there's many other ways, many other things that you could implement here. Is this even the right thing to do? Should we even be looking at at these non-parametric pipelines or not? Yeah, so this is what I would be very happy to discuss. And I hope I didn't bore you too much with astrophysics. Right, so I think in the interest of time, I will not read out my conclusions. Thank you very much.
Do you have any questions about cosmology and or Post-Bayes?
What about that Hubble constant? What's going on?
Oh, I had a slide about that. But
Oh, that's good.
I mean, so I will show you the slide because I think it makes a good point about how we have to be really careful these days. Huh? How can I show this? Okay, so the Hubble constant tells us the expansion rate of the universe today, and we have two different measurements. Now we have one from the early universe, which comes from the CMB, and we have one from local stars, so to say. So we just look at distances actually. And as the data gets better and better, or as our statistical errors go lower and lower, we start to see that these two probes seem to be in tension. Yeah? And now it's very, very important, and this is a very big discussion in my community, to make sure that there are no unknown systematics, especially in the supernova measurement. Yeah? So maybe there's an angle here, right? So maybe if you can give me some peace of mind in the posterior you produce here, and non-Bayesian posterior you produce, and you can give me peace of mind in case there are model misspecifications that look like this, that I'm still robust to this, I think this would be interesting. I don't know, I hope that was, I'm just saying stuff there.
Do you have any other questions?
Have you looked at any more efficient estimators of the MMT? Because you mentioned the computational costs.
Yeah, exactly. I mean, no, we haven't, right? So we only did this. But yeah, again, so we talked earlier. I mean, so what I would really want, which might not be possible, would be something that works with like even fewer simulations than this, or observations actually, right? So the simulations we can try to make faster, but observations we really only have a few, or actually one. But yeah, no, we haven't looked at this. Please tell me about this.
We should check it.
Definitely.
One thing that I wonder about here, and obviously, unlike you, I'm not an astrophysicist, so I don't know anything. What kind of model misspecification are you actually worried about? Because I think a lot of the work we've been doing is focused on things that are sort of mathematically elegant or convenient to study. But here it seems like you actually have like a good idea of the type of, modes in which you might be wrong about the model. And I would wonder, we should probably have a chat about that more afterwards, but I wonder what kind of misspecification you're actually worried about here.
Yeah, I mean, to some degree, right? So the fact of the matter is, like when I look at the summary statistic here, the more I go to the right side, the less certain I am about my predictions. And it's really about pushing the part of the data vector by inference further to this side, right? And I'm not sure if I can. Yeah, maybe I can give you attempt to give you a functional form for this, which would be my best guess about this. But yeah, so I know where the misspecification will happen. I'm not sure about kind of the functional form of this, but I can attempt. I can do my best, so to say.
Well, if there are no further questions, we have lunch now for an hour, and we'll be back afterwards with some packed days.
Thanks.